Hello and welcome to a new video on IGCSE Physics Classified Paper 4. In this video, we shall be discussing the topic of the universe. We will begin with general concepts. Give an estimate for the diameter of the Milky Way galaxy. So the Milky Way galaxy has a diameter of approximately 100,000 light years. This is something you need to know as a piece of information. It would take light approximately 100,000 years to cover the diameter of the entire Milky Way galaxy. Next, we move on to the topic of redshift. The Milky Way is one of many billions of galaxies. Each galaxy contains many billions of stable stars. On the Earth, light from a distant galaxy is observed and analyzed by astronomers. This information is used to determine the speed at which the galaxy is moving away from the Earth. Describe how the observed light is different from when it was emitted. State the quantity that astronomers use to determine the speed at which the galaxy is moving away. So, first of all, the observed light has a longer wavelength, which is shifted towards the red end of the spectrum. This is the idea behind the concept of redshift. The idea is that because these galaxies are so far away, the wavelength of the light emitted from the distant galaxy is observed to be shifted more towards the red end of the spectrum. So you should know that there are 7 subspectra of light in a sense: red, orange, yellow, green, blue, indigo, violet. And before red, you should know from other chapters that we have infrared. And then after violet, you should know that we have ultraviolet. And you should know that as we move in this direction, lambda decreases and frequency increases. So from far away galaxies, the light seems to be shifted in this direction towards the red. So if something was originally yellow, it might have a more orange glow. If something was originally blue, it might have a more green view. So what does this indicate? This idea of redshift, this idea that the wavelengths are shifted towards red, that they increased, this tells us that galaxies are moving away from the Earth. And in fact, using some calculations, it might enable us to determine the speed with which the galaxy is moving away. So what quantity is underlying the concept of redshift? Redshift. So shift means change, and change in what? Change in the wavelength of the observed light. Light from a distant galaxy is redshifted. Explain what is meant by redshift. State the quantity that the redshift of a galaxy is used to calculate. So this is the other way of saying the same thing. So in the previous question, we were told what? So let's look at the previous question. We were told in double I, state the quantity that astronomers use to determine the speed. And the answer was the change in wavelength, which is redshift. In this question here, in double I, we're told state the quantity that redshift is used to calculate. So that's the opposite of it. The answer would be the speed with which the galaxy moves away from Earth. So you should understand that redshift or change in wavelength are used to calculate what? The speed of moving galaxies, moving away from Earth in a sense. So what is redshift? We said that it is the increase in wavelength because it moves towards the red, and we said that the red has the longest wavelength in all the colors. So it is the increase of wavelength of light from distant galaxies as they move away from the Earth. So the words that are in air quotes are the keywords that are necessary for you to get the mark. Again, it has to be an increase of what? Of wavelength of light from distant galaxies as they move further away from the Earth. And this redshift helps us determine what? It helps us determine the speed with which the galaxy is moving away. State and explain what can be deduced from the redshift observed by astronomers in the light from all distant galaxies. Again, it's a third way of asking the same question. Here we have a more detailed explanation. So what happens exactly? How do they assess the speed of the galaxy? First of all, they compare the wavelength. So the wavelength of light from a distant galaxy is compared with the wavelength on Earth. And we see that the one coming from the distant galaxy is larger. It has a larger wavelength, shifted towards the red end of the spectrum. So how do we make use of this? This tells us that the distant galaxy is moving away from the Earth. And the fact that the galaxy is moving away from the Earth means that long ago it was closer to the Earth than it is right now, which tells us what? It tells us that the universe is expanding. So this is the summary of what redshift is and how it helps us understand the universe. Galaxy Q is twice as far away from the Earth as Galaxy P. Suggest how the speed of Galaxy Q relates to the speed of Galaxy P. And explain how comparing the speeds of the two galaxies provides evidence for the Big Bang theory. So let's start with IV first. So for IV, we know that Q is further away than P. And because it's further away, we will see that it shows a greater redshift, as we said before, and this tells us that it's traveling at a greater speed. This tells us that the universe is expanding, and we can understand from that that the universe was initially a single point, which is what the Big Bang theory is all about. It says that the universe was initially a single point, and it expanded over the years to form the universe in which we now live. And what about the speed of Galaxy Q and the speed of Galaxy P? We are going to study this further later on in this same video. We have something called Hubble's constant, and it relates distance and speed. So h naught equals speed over distance. And this tells us that the greater the speed, the greater the distance. Or in other words, the greater the distance, the greater the speed. So since Galaxy Q is twice as far away, the speed of Galaxy Q must be almost twice the speed of Galaxy P. And we're going to discuss in more detail how V and D are related exactly and what calculations we can use in order to figure this out. State one measurement that is taken when determining the speed V at which a galaxy is moving away from Earth. We said that the speed V is related to redshift. Redshift tells us the speed of the galaxy. Write down an equation relating V and D, where D is the distance of a faraway galaxy. Again, we said that Hubble's constant, which is h naught, is equal to the speed over the distance. And the unit here would be like 1 over time, so it would be like per second, or like second negative 1 would be the unit of Hubble's constant. State how the distance d of a far galaxy can be determined other than by using the equation in double I. So in double I, we could determine the distance of the galaxy using the speed, and we get the speed from redshift, of course. So what other way is there of determining the distance? Another way of calculating the distance or determining the distance is from the brightness of a supernova in this galaxy. If you check out the video on stars, you will realize that a supernova is a form of a star. It's an explosion of one of the large-sized stars as they evolve in their life cycle. Next, we move on to another piece of evidence for the Big Bang Theory, which is CMBR, cosmic microwave background radiations. State when cosmic microwave background radiation was formed and where we detect it coming from. So when was it formed? It is theorized that CMBR, or microwave background radiation, was formed at the beginning of the universe, right after the Big Bang. And where do we detect it coming from? We detect it coming from virtually everywhere, from all points in space. Describe and explain what can be deduced from cosmic microwave background radiation, or CMBR. So this CMBR is observed, like we said, at all points in space around the Earth. And this radiation has expanded into the microwave region of the electromagnetic spectrum. So what can we deduce from this? This tells us that the universe has expanded. Give two pieces of evidence for the Big Bang theory and explain how this evidence supports the Big Bang theory. So like we said, there are two pieces of evidence here. First of all, redshift, and second of all, CMBR. Redshift, as we said before, says that the further the galaxy away from Earth is, the greater the redshift we see from the light coming from it. And if the redshift is greater, this tells us that the galaxy is moving faster away from Earth. So what does this tell us? This tells us that the speed of galaxies is directly proportional to their distance from Earth. So if something is further away from Earth, it will be moving at a greater speed. And this tells us that the universe has expanded from a single point, which is what the Big Bang theory is all about. The second piece of evidence is CMBR. And because CMBR appears to be coming from all points in space, and it's the same in all directions, this tells us that all of these were actually a single point long ago. They were in contact a long time ago. And as the universe has expanded, the wavelength has increased and reached the microwave region of the spectrum. Remember, we have radio, micro, infra, visible light, and then ultra, X, and gamma, and whatever. So we're moving towards greater wavelength again. And this tells us that the universe has expanded and that it was also significantly hotter long ago. Hubble constant calculations is the final section of this video. Now we get into a bit of mathematics. State what is represented in space physics by the symbol h naught. We said that this is Hubble's constant. Write down an equation that defines h naught in terms of speed that the far galaxy is moving away from Earth and its distance from the Earth. We said that the equation is h naught equals v over d, or like 1 over time, which therefore the unit would be 1 over second, or second power negative 1. This would have also been the correct answer here. Just writing s power negative 1 would have also worked. And they gave us the numerical value here. And in III, they're asking us to estimate the age of the universe in seconds. So how do we get the age of the universe? The age of the universe is the time it has taken, right? And what do we know about time? We know that time is distance over speed, because distance equals speed times time. So we can deduce that time is distance over speed. So in another sense, we can deduce that time is actually 1 over h naught, because h naught is sort of like 1 over time. So therefore, if you want the time, like the total time taken in the universe, what would that be? That would be 1 over h naught. So all we have to do to get the age of the universe is to basically calculate this number here, 1 over 2.2 times 10 to the power of negative 18, which gives us 4.5 times 10 to the power of 17 seconds. So an estimate for the age of the universe is roughly 4.5 times 10 to the power of 17 seconds. Now, one might ask, how is this a fixed number? Isn't the universe increasing in age as we progress in time? Well, you can consider that. Yes, it's correct. But the idea is that this is an estimate, and with time, of course, this changes. However, as you can tell, this is a huge number. So for significant change to occur, this will take a very long time, because this is already in 10 to the power of 17, which is billion, whatever. So my guess is, with time, the value of h naught itself is going to change, and therefore the age of the universe will change as well. But currently, within a limited amount of time, say 100, 1,000, a million years, you don't really notice a significant change in this number, because, like I said, this is a huge number. So a million years from now, this would not really matter. It would be like some 4.4.5000001. That's a million years from now. So again, this would not be a significant change. So anyway, for now, the age of the universe is 4.5 times 10 to the power of 17. In this question, they tell us the Hubble constant is equal to 2.2 times 10 to the power of negative 18. Calculate the distance from the Earth of a galaxy that is moving away at the speed of 1.3 times 10 to the power of 7. So how would we do that? We would use the equation. What is the equation? H naught is V over D, like 1 over time. It's velocity over distance. If we want to get the distance, so let's isolate the distance in this equation. So let's just take the distance up. So d H naught equals V. So d equals V over H naught. So by dividing the speed over the Hubble constant, we can get the distance. So this number goes on top. This is the speed. And then the Hubble constant goes at the bottom. And you just divide these two numbers together. And you get 5.9 times 10 to the power of 24 meters, of course. Calculate an estimate for the age of the universe and give your answer in years. Like we said, the age of the universe is basically time. And we know that H naught is 1 over time. So time would just be 1 over H naught. And 1 over H naught is calculable. You just do 1 over the number that we're given, and we get 4.5 times 10 to the power of 17 seconds. We want to convert this number into years, so we divide by the usual set of numbers, 365 for days, 24 for hours, and 64 minutes, and 64 seconds. So if you divide this by that, you get 1.43 times 10 to the power of 10 years. So basically 1.43 times 10,000 million years, or like 10 billion years, exactly. So we've been around, or the universe has been around for around 14 billion years, according to this theory. A galaxy is moving away from Earth with a speed of 33,000 kilometers per second. The value of the Hubble constant is 2.2 times 10 to the power of negative 18 per second. Calculate the distance from the galaxy to the Earth. Give your answer in light years. So first of all, we want to calculate distance. So we use the equation H naught equals V over D. We are given V, and we want to get the D. So we can rewrite the equation here. We take the D to the left. So D H naught equals V again. So D equals V over H naught. We have the V, 33,000 kilometers per second. And the value of the Hubble constant is this number here. So if we divide them by each other, we get 1.5 times 10 to the power of 22 kilometers. You can multiply by 1,000 to get the distance in meters, and this would be the distance in meters. Now, what is 1 light year equal to? Light year is a distance, not a time. I know it says year, but it's still a distance, not a time. So it's equal to speed of light multiplied by time of 1 year. Speed of light is 3 times 10 to the power of 8. Time of 1 year is basically, like we said, 365 times 24 times 60 times 60. If we multiply those by each other, we get this number here, 9.46 times 10 to the power of 15. All we have to do now is divide one distance by the other, because 1 light year is the distance traveled in 1 year, and we want to know how many light years it would take to travel this distance here. So you simply divide this one by that, and you get 1.6 times 10 to the power of 9 light years. So for light to reach Earth from this galaxy, it would take around 1.6 thousand million light years. So 1.6 billion light years. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.